Hello, here I am today with two of the world's most eminent climate scientists, Dr. Jerry Meehl from the National Centre for Atmospheric Research and Professor David Karoly, who is an emeritus professor at the University of Melbourne. I've known both of them for a long time. They've known each other for many years. And today we're just really wanting to talk about the early years of Southern Hemisphere meteorology and climate. So welcome, David and Jerry. So today you are, as I said, some of the most eminent climate scientists in the world, but back in the 1970s, you were both early career researchers. So I just was wondering if you could describe some of the research that was going on back then and who were the people that you were working with and exploring Southern Hemisphere meteorology.
Yeah, so I got into it from one of my advisors and mentors, Harry Van Loon. And so he was a prominent in-car climate scientist in those days. And so I would go into the map room. We had a synoptic meteorology map room with weather maps, and he'd be in there. And he was always looking at the tropical map, looking for what was going on with El Nino. And then the tropical map would extend down a little bit into the Southern Hemisphere, and he'd always be looking at the subtropical high in the South Pacific and looking at these things that were connecting Australasia to the Pacific. And he would be in there ranting and raving about how various things were going on, and I was trying to pick up what he was talking about. But then he would always be talking about the Southern Hemisphere, and he'd done all this work in the Southern Hemisphere weather and climate, and he was really an expert in that area. And so that's kind of where I got interested in Southern Hemisphere meteorology and climatology, was from Harry.
And I was an Australian undergraduate student in maths and physics in the early 70s, and was trying to work out what I was going to do, because I was always interested in outdoor activities and hadn't really thought about doing anything in weather and climate at all, until I realized that I could apply the maths and physics that I was finding really easy and interested in to understanding the behaviour of the atmosphere and the ocean. I was lucky enough, when I finished my undergraduate degree, to get an opportunity to go and study for a PhD in the United Kingdom. And got the opportunity to do a PhD fully funded from Australia in the United Kingdom with Brian Hoskins, who was an outstanding, at that stage, early career researcher. I was his second PhD student. He's now been knighted, Sir Brian Hoskins. And I just happened along with all my expenses paid, all my funding paid, looking for a project to work on. And he suggested that I should do, having a maths and physics background, do some work to looking at the theoretical basis for what are called teleconnections, or linkages between climate and weather, if you like, variations, and how they would link across different parts of the hemisphere or across the whole globe, particularly things like ocean temperature variations, or even winds blowing over the mountains affecting planetary waves, or what are called stationary waves, seasonal variations across different parts of the globe. I started working on that and was doing the theoretical analysis as well as the numerical modelling simulations in an idealised framework. And these were being compared in the Northern Hemisphere with observational data. And I finished my PhD in 1980, came back to Australia in 1980 and got a job in a research centre called the Australian Numerical Meteorology Research Centre. And what I wanted to do, recognising that at that time there were these weather forecast analyses that were being used to verify the theoretical work that I'd been doing, thought we needed was Southern Hemisphere datasets good enough to verify what the theory suggested should be similar sorts of teleconnections in the Southern Hemisphere. So let me finish there. I had a job jointly between Bureau of Meteorology and CSIRO starting in 1982.
So just picking up on what you were saying, Jerry, you were talking about Harry Van Loon, and he was originally from South Africa, wasn't he? And said
Denmark.
He was from Denmark, right?
Yeah.
But there were David's talked about the Australian activities going on there, and there were also people in South Africa doing some research, obviously, into Southern Hemisphere meteorology.
Yeah, so Harry went down to South Africa, and he's working for Talyard. And one of the things he was doing, and this is the 1950s, he was analyzing observed weather data coming in from whaling ships. And the whaling ships would be circling the Southern Hemisphere and the Southern Ocean, obviously trying to catch whales. And a side benefit of that was they were reporting weather observations. And so one of Harry's jobs was, and he was working for the South African Met Service, and he was getting these weather reports from these whaling ships, and he was drawing these synoptic meteorological maps of the Southern Hemisphere. And these are the first that had ever been done this way, because this is the first time they really had data that was really well distributed around the Southern Oceans. And it was a real art form to draw these maps, because you have these scattered observations and you kind of fill in the lows and the highs and the fronts and things like that in a very imaginative way, but basically physically based. So you weren't making stuff up. You were doing things that, it was basically a mental reanalysis, what we do now with computers. They were doing by hand by eye, and filling in and making these really detailed synoptic meteorological maps. And so he did that in South Africa for a number of years. And so that's when he really got interested in a lot of these things going on in the Southern Hemisphere. And he could see, after you look at daily weather maps over several months or a couple of years, you can kind of get a feeling for the climate also, kind of where the storm tracks are, how the circumpolar trough was behaving. He noticed that there seemed to be that the circumpolar trough would expand and contract twice a year. And that got him onto a topic called the semi-annual oscillation, where he identified this is kind of an interesting feature of this seasonal cycle in the Southern Hemisphere, mid and high latitudes. And so he kind of picked up on a lot of these physical things that he kind of learned as he went, what was going on in the Southern Hemisphere in terms of meteorology, and then some aspects of climate.
Yeah, because I guess that's a unique feature of the Southern Hemisphere, is so much of it's ocean, right? And so there's not much data below, 40 South in Australia, and so these whaling data, were they all over the Southern Ocean?
Yeah, they're all over the Southern Ocean. They were mostly in the warm seasons, unfortunately, because the whaling ships would kind of leave during winter, but they had coverage for maybe 2/3 of the year. And that was enough to give them an idea of kind of what was going on in terms of these weather systems in the Southern Hemisphere, kind of where the storm tracks were for the first time, got a feeling for that, because very few islands, it's all ocean, right? So the only way you get data from that time period was from ships. And so the fact that there was a big whaling fleet in the Southern Oceans, not good for the whales, but really good for weather data from that time period.
It's important to understand also that there were routine shipping routes for freight and for tourists and for passengers between some of the major ports from the Northern Hemisphere into the Southern Hemisphere, but they didn't span the whole ocean. So there were large remote areas, throughout much of the 20th century, between the two wars, and then even after the Second World War, there were still major data gaps where there were just no regular ships. And actually, as the whaling industry declined between the wars and then after the Second World War, there were massive data gaps. There's a small number of islands that were reporting the data, but often the data wasn't provided rapidly. So what was needed for providing weather forecasts, for instance, in Australia, most of the weather systems in the Southern Hemisphere, as well as in the Northern Hemisphere, move in the mid-latitudes from west to east. That means the Indian Ocean. There weren't many ships routinely travelling from South Africa to Australia. There were ships travelling from Australia through the Suez Canal to Europe or to India, things like that. Not many ships. That meant that there was a massive ocean gap. And that couldn't really be filled except by experts who would follow ship reports of, say, low pressure systems, who could then track them by other ship reports.
Yeah, and so then I guess they were also supplemented by some field campaigns. And Jerry, you were involved in some of those early field campaigns in the 1970s.
Yeah, so the first thing I did, I finished my undergraduate degree in 1974 at University of Colorado, and I'd been working as a student at NCAR, and that's where I met Harry Van Loon. And because I was at NCAR, I heard through the grapevine that they were going to be hiring lackeys like me with little kind of undergrads to go out to these remote locations and launch these constant level balloons to study atmospheric circulation at about 150 hectopascals. They're up pretty high in the troposphere. And so I kind of weaseled my way into this project and got hired. and it was called the Tropical Wind Energetics Reference Level Experiment, or TWIRL, T-W-E-R-L-E, or twirly, as David would pronounce it, depending where you're at. And so the idea was Paul Julian, later of Madden-Julian oscillation fame, it was an NCAR scientist. He was the chief scientist, and he was interested in the upper level winds, not only in the tropics, because he's already interested in intraseasonal variability in the tropics, and he thought if he had enough of these constant level balloons, they would go up to about 150 hectopascals and be neutrally buoyant there. They were big mylar plastic balloons, and then they would just be carried around at that altitude by the prevailing winds, and then he could track what the winds are doing, and maybe the balloons would kind of cluster or do things. He could kind of ascertain behaviors of what was going on in the upper atmosphere that you could get from these better distributed observations that you couldn't get from just stationary and widely scattered weather stations or launching weather balloons. So there was 3 stations. There was one in Pago Pago in American Samoa, one in Ascension Island in the Atlantic, in the tropical Atlantic, and one in Accra in Ghana. And so we all got trained, we got hired, got trained. There was about 5 or 6 people at each site. They sent us out there. There was a very elaborate procedure too. There was about 10 instruments on each balloon. You had to test them all, tie them all together. There was a special launch vehicle. You'd go drive down the runway, so you had a 0 wind environment, and hand over hand the balloon and the instruments that would go up. And then that would be it. That'd be the last we'd see of them. They would broadcast their data to a satellite. One of the Nimbus satellites would be relayed to Goddard Space Flight Center, which would be relayed to NCAR in Boulder. And this guy named Dennis Shea, who was working for Paul Julian, would take those data as they came in and produce plots, first in the tropics and during the tropical phase of the upper level winds, which was one of the first really nicely kind of articulated upper level wind maps for the tropics. We did that for about 5 months from the tropical sites, and then we shifted to Christchurch, New Zealand, and NCAR was maintaining a balloon launching facility in Christchurch because Vin Lally, who was kind of the head of this balloon group at NCAR, he was always interested in these constant level balloons that could be carried around the hemisphere on the prevailing winds. The trouble with the Northern Hemisphere was there was these communist bloc countries that didn't like things flying over their territory. So to do these kinds of measurements, you pretty much had to do them in the Southern Hemisphere. And so NCAR for many years had a facility in Christchurch where they did these various balloon experiments. So the twirl was one of the ones we did from there. So we were launching balloons from there, and those were then kind of preferentially carried around in the Southern Hemisphere mid and high latitudes, and that produced some of the first maps of upper level winds in the Southern Hemisphere mid and high latitudes from those kinds of balloons. So later on, of course, Paul Julian, when he was analyzing the tropical tracks of these balloons, they would actually cluster in certain places and kind of move along with a kind of a 30 to 50 day kind of period. And so that was one of the early indications he had of this intraseasonal variability in the tropics, which later got named the Madden-Julian oscillation for he and Roll Madden, who kind of quantified this in a more kind of detailed way. But this is one of the first kinds of pieces of evidence he had that this was kind of happening.
So you part of the
Well, yeah, of course, at the time, I had no idea what was going on. We were just launching these balloons and trying to survive in these various interesting locations. But yeah, and so the guy, Marcel Verstrady, who was the guy that the NCAR employee who was running the station in New Zealand, he lived there for, I don't know, 25 years or so, and he became the longest serving NCAR employee. He finally retired during COVID because he didn't want to work from home at age 90, and he was still a full-time employee working at NCAR at that time because they brought him back when the Iron Curtain fell. Then it was okay flying balloons around the Northern Hemisphere. They closed down the Christchurch facility in the late 80s, and he came back to Boulder, and he served the rest of his career in Boulder.
What a great story. And David, you were saying you were doing some of the first analyses of the Southern Hemisphere, and there was this GARP experiment, right?
That's right. And so let's go back a little bit. I mean, what had been done in the Northern Hemisphere because of the greater land coverage, more people, more weather stations, it was possible to do what were called gridded, regular grid of analysis of the weather patterns at the surface and at multiple layers through the atmosphere, but only to the equator. They only did it for the Northern Hemisphere, and that really existed from the 1960s onwards. And the data had been analysed and used to look at month to month and year to year variability, particularly the patterns of weather systems, but particularly seasonal changes and the year to year changes, that allowed us to sort of simulate or understand from the weather data these teleconnections from, say, ocean temperatures, El Nino and the warm ocean temperatures, and how they link to weather variations over North America, and particularly from the tropical Pacific out to North America. There was a similar expected pattern from the tropical Pacific over South America, and also links that were expected and understood between El Nino and weather variations over Australia and rainfall changes. But there didn't exist gridded data sets over the Southern Hemisphere, just because of the greater occurrence of oceans, larger oceans. But what was done when satellite data became available, the scientists and weather analysts, I guess that's right, were trying to prepare gridded weather analyses over the whole of the Southern Hemisphere, filling in some of the data gaps with temperature data from the satellites, and also trying to represent the locations of the low pressure systems where there would be clouds. Those sorts of analyses were made available almost as soon as satellite data became available from the late 1960s and early 1970s, taking into account the temperature data, but also what are called proxy data or pseudo observations to locate the low pressure systems from satellite imagery. Those were inserted into the locations over the oceans, and then Australia was the first, if you like, the Bureau of Meteorology in Australia prepared these daily and multiple times a day gridded analyses that were then able to be consolidated for 10-year periods. By the end of the by early 1980s, there were 10 years of these analyses available, daily data. We prepared those into looking at the year-to-year and day-to-day variations to represent the circulation variations, the climate variations, and looking at that in much the same way as had been done in the Northern Hemisphere. And then by the end of the 1980s, I was able to prepare the sorts of analysis that was required to confirm that the theoretical understanding of what we expected in the Southern Hemisphere would be able to be assessed, evaluated, and then we showed that it could mirror exactly what was found. The spatial patterns, different because of different land masses and different mountain ranges, but actually the teleconnections from tropical Pacific over South America were identified, and similarly the patterns that linked to rainfall variations over Australia associated with El Nino, as well as the other common variation in the Southern Hemisphere, which is the strength of the westerly winds that span all around the Southern Hemisphere, a pattern that was called the zonal index initially, but more recently has been called the Southern Annular Mode, because some Northern Hemisphere scientists decided that we couldn't use the Southern Hemisphere name, the zonal index, but use the Northern Hemisphere name, which was the Northern Annular Mode, and therefore we had to have a Southern Annular Mode, which was the, if you like, common thing. And that work on annular modes was taking place in the Northern Hemisphere in the 1980s, and as well focused on the Southern Hemisphere variability. But there were scientists in New Zealand, Kevin Trenberth and John Kinson, who'd been doing work on Southern Hemisphere variability, particularly the circulation variations, together with work that Harry Van Loon had been doing on circulation variations, this semi-annual oscillation as well. And so work had been done, and I was collaborating with Kevin Trenberth on what he was doing in terms of the analysis of the mean seasonal and year-to-year variations. He was also looking at what were these zonal index variations as well, changes in the zonal winds.
Yeah, and I think that SAM research is still really does rely on some of those station observations, right, in the islands over the Southern Ocean. And
it does. It much more now makes use of what are called global analyses. But if we want to look at longer term periods, the other aspect of this was that what is now called reanalyses, the combination of the same numerical weather analysis systems using weather forecast models was expanded from the Northern Hemisphere, separate from the Southern Hemisphere, to be global analyses in what was called the first GARP global experiment, which was to prepare global weather forecasts, global analyses, took place at the end of the 1970s, 78 and 79. That was a numerical modelling or numerical analysis experiment. There were some extra stations that were set up in remote areas in this FIGI, first GARP global experiment. Scientists don't like long words. They like to come up with 4 or 3 letter acronyms. So FIGI was this first GARP global experiment, prepared analyses that were for the whole globe. And after that, 10 years later, there was an effort to try to go back and redo the early analyses pre-79 and 78, back to when the satellite data became first available, and even before that to do global analyses right back before the Second World War. Their quality was better from 1950s onwards when there was upper air data, when there was satellite data. The really interesting thing was that these Bureau of Meteorology pseudo observations of surface pressure and the locations of the low pressure systems, when it was sent to the United States, the Australians used a different east-west longitude orientation, and the locations of the Australian Bureau of Meteorology's interpreted pressure data, pseudo observations, was shifted or reversed. So the plus and the minus longitudes were reversed, and they were shifted effectively by up to 90 degrees east or west of where they should have been, and sometimes as much as 180 degrees if they were close to the date line. So it turned out to be there was a significant mistake. It only applied in the Southern Hemisphere and only applied for the period from the 1970s to the 1980s, when there was enough satellite data and those were no longer ever used.
The joys of international cooperation.
As well as the joys or the absence of data in the ocean regions of the Southern Hemisphere pre-satellite data.
So, Debbie, you touching on these teleconnections from the tropics to the Southern Hemisphere extratropics, and I know, Jerry, you were involved in some field campaigns looking at the Australian monsoon and then following on, I guess, later into the 80s about looking at El Nino and Utah.
Yeah, well, kind of the lead up to that was when I came back from the Twirl project, I ended up starting a master's degree at the University of Colorado, still working at NCAR as a student. Harry Van Loon was my advisor. And so he was working at that time on something he called the Greenland Seesaw, which was actually the North Atlantic Oscillation, but he wanted to coin his own term. And this is something, being Danish, he grew up knowing this, that there was Danish immigrants that were living in Greenland, and when they were writing letters back and forth, they noticed that when there'd be a warm winter in Denmark, it'd be really cold in Greenland, and if it was warm in Greenland, it'd be really cold in Denmark, and it seemed to seesaw back and forth. And this is just an aspect of how the atmospheric circulation sets up in the North Atlantic Oscillation, what we call the NAO now. So he wanted somebody to look at connections to the tropics and possibly to the Southern Hemisphere. So he got me on that. And so I was doing things like looking at station pairs, going back in time, and you get a station pair and look at the sea level pressure and you infer the winds blowing in between those two stations. And so I was looking at like Hawaii and looking down at Tahiti and some of these other stations down into the Pacific. And that was all kind of interesting, and it did all seem to be connected in some way. But my big breakthrough, my one thing I remember was my first kind of scientific result was, he said, well, look at some African precip and see if you see anything in that. So I was looking at these stations from African precip, and I was looking at Southern Hemisphere summers, so it'd be kind of South Africa, and there's the kind of the big rainfall maximum across the kind of southern part of Africa. And it seemed like, depending on the phase of the North Atlantic Oscillation, that it would shift a little bit. And it was a latitudinal shift, and it was something Harry hadn't even anticipated. I thought, wow, I actually discovered something here. So I was all excited about that. But that was a connection with the NAO down to Southern Hemisphere rainfall over Africa, which is kind of interesting. So then kind of finished the master's degree then, and then I had my kind of antenna up for another field project, and this monsoon experiment was coming up. And it was going to be a huge international monsoon experiment. And they're getting a lot of funding for it, and a lot of prep and build-up and everything else. A lot of money was flowing. And so they needed people to go out and deploy equipment. And so they had come up with these portable weather stations where you can launch a radiosonde balloon as well as take observations. And so they wanted to deploy these in data-sparse areas. And so there was 2 phases to the monsoon experiment, which was called MONEX, monsoon experiment, MONEX, winter MONEX. And of course, these are Northern Hemisphere people naming these things. It's actually the Australian monsoon, or Australo-Australian monsoon, whatever you want to call it, and summer MONEX, which would have been the South Asian monsoon. So winter MONEX was for December 1978, January, February 1979, and then summer MONEX would be the monsoon season in South Asia, June, July, August of 1979. So I got sent out to the north coast of Borneo to deploy this portable weather station in this little town of Bintulu on the north coast of Borneo, which was going to supplement some ships that were going to be out in the South China Sea. And then there was going to be some other weather observations. The other NCAR crew was up in Palawan Island in the southern Philippines. So we had those 2 points, and they were supplementing the other radiosondes and the ships out there in the South China Sea. And the idea was to monitor cold surges coming off of Asia and how they would get all the way down into the monsoon area and trigger either little vortices or cyclogenesis or tropical cyclones in the South China Sea, or even affect rainfall over Borneo even further south, and even getting down all the way to northern Australia. So that was a real big thing. But there was some equipment at Bintulu, my site. So I get there and I'm setting up this equipment. There's a real long story that goes with that, but to make it short, we also had the Doppler radar from MIT, Massachusetts Institute of Technology. So they were going to try to get good Doppler radar measurements of these convective systems over the South China Sea to the north of us. We're facing north there. And they were going to document what was going to happen with these cold surges. And so we were launching balloons twice a day at the standard 2 observation times. And then if we went into an intensive observing period, we'd have to launch 4 times a day, which was pretty relentless. So anyway, we're down there, and the thing that we first noticed right away was this interesting diurnal cycle. So we'd wake up in the morning in this crummy hotel we're staying in, walk to the airport. The airstrip was right in the middle of the little town of Bintulu. And we look out, and there'd be a line of cumulonimbus clouds paralleling the coast just north of Borneo there. Big cumulonimbus clouds, 8 in the morning. And then about noon, they die out. And then over the inland Borneo, then you get these big cumulonimbus clouds coming up in the afternoon. And it would just go back and forth. And apparently this was a feature of all these big tropical islands in the maritime continent. And we thought, well, this is a mechanism to have round-the-clock convection. You'd always think of the diurnal cycle of afternoon convection over these big islands, but you'd have these offshore things, and what was happening was the north coast of Borneo faced north, and so the trades are coming in from the northeast, and so at night, the inland would cool, you'd get a land breeze, the flow would be just going offshore, but you'd have intersection with the large-scale flow, you'd get convergence right off the coast. That convergence would cause these big cumulonimbus clouds to pop up. And then when the land would heat up during the day, then that would die down, then you'd have the big convection over the center of the island. So that was one of the things that the MIT radar was able to document. And then they looked at satellite maps, and they could see that happening around a lot of these islands in the maritime continent. So that was kind of interesting. So anyway, that was kind of trying to document these kind of aspects of the monsoon in that, for the Australian monsoon. There was an interseasonal variability part to it. There was an MGO part to it, and we'd get alerted if there was an MGO event that looked like it was coming along. There wasn't a big awareness of the MGO at that time, though. That was a new thing, pretty much, because the MGO literature started in the mid to early 70s. It was mainly these cold surges they were very interested in. So that, I think, was an interesting part of that. There was aircraft they had flying around, so they were trying to take measurements of convective processes, flying airplanes around these things. And so that was probably the biggest connection to the Southern Hemisphere and the tropics. And then summer MONEX was the same kind of thing, but for the South Asian monsoon.
And was there any connection to?
Well, they were worried about that, and there was this kind of weak kind of El Nino in the late 70s that people argued about whether it was an El Nino or not, and then that kind of entered into the interpretation of some of the MONEX data. But it didn't seem to be, it was mainly on convective processes because the GATE project had occurred in the tropical Atlantic, and that was one of the first big field experiments, and that was like in the early 70s, like 74. That was one of the first big field projects where they were trying to measure convective processes with the idea of trying to get these better depicted in models. And then they were there was a lot of people that were on GATE that were in MONEX, and they had that same mentality. They were going to go out there and measure convective processes now over this monsoon area and see how different it was from the tropical Atlantic.
I mean, it's also important, I think, to remember that the oceanographers were talking a lot about El Nino and its opposite phase, La Nina, but the atmospheric scientists were talking about something that they thought for a while was independent, called the Southern Oscillation. And Southern Oscillation was if you like, a teleconnection of atmospheric pressure variations between the Indian Ocean region, centered around essentially southern India, and the far, if you like, Tahiti and the far eastern Pacific Ocean. And it was centered on the equator, but for a while at least, the groups of scientists looking at the two were thinking about them sort of almost independently. And it was really only in the late 1970s and early 1980s that the connections between Southern Oscillation and El Nino were well understood. And in particular, there was very strong El Nino event in 1982-83 with major impacts in Australia, in South America, and in North America, and in India, that led to recognition that these Southern Oscillation variations and El Nino variations were very closely linked, and then a massive blossoming of research to better understand the connections, both El Nino and La Nina in the ocean, and the atmospheric variations that went on with them, and their connections not only in the Northern Hemisphere, but into the Southern Hemisphere as well.
Yeah, and you have to remember that there weren't a whole lot of observations of sea surface temperatures that were really good at that time. There was a big awareness of the 72, 73 El Nino because that had such a huge impact on India. There's a gigantic famine, and it must have affected Australia at that time.
It did.
So going into something like MONEX, the 72, 73 El Nino was only 5 years before that, and people weren't as really obsessed with it at that time. And in fact, the first paper that really described a canonical El Nino event was the Rasmussen and Carpenter paper in 1982. And they had this Eastern Pacific El Nino that formed along the coast of South America. And they knew that these events affected the anchovy industry along the coast of Peru, and they knew this warming was taking place right along the coast of South America. But they documented this warming that would actually extend well across out to the date line. So it was a much larger scale phenomenon. And of course, what happened was the paper came out in 1982. There was immediately the 82, 83 El Nino that was different from this canonical El Nino they just described. And so there's a lot of kidding of Gene Rasmussen. Say, well, Gene, here you just come out with this paper and you described it. And now that we got this one 82, 83, it's totally different from what you described. And he goes, yeah, well, the minute you start describing something different's going to happen.
And look, one of the other things that happened in 1982-83 in particular was the first international conference on Southern Hemisphere meteorology, which was taking place in Brazil at the time that an El Nino event had reached its peak and was just starting to wane. But no one knew at the conference really that it was happening. And so it's an interesting connection between this development of science and the growing interest in meteorology of the Southern Hemisphere and connections with the tropics and connections to the Northern Hemisphere across the different countries and continents in the Southern Hemisphere. The first gathering of meteorologists working on Southern Hemisphere meteorology that was initiated through the American Meteorological Society 3 years before, had decided to set up a committee on meteorology of the Southern Hemisphere, the Southern Hemisphere Meteorology Committee under the American Meteorological Society, and then to hold an international conference, not in the United States, even though it was the American Meteorological Society, but to hold these conferences in the Southern Hemisphere. And the plan was to run the conference. It was essentially led by a group of either expatriate Southern Hemisphere scientists who were based in the United States or connected to some scientists in the Southern Hemisphere, but almost all of the planning was done by expatriate Southern Hemisphere scientists who were living in the United States at the time through the American Meteorological Society, and to run the conference in Brazil, unfortunately, or perhaps in hindsight, fortunately, at the time an El Nino event was actually occurring.
Actually, a little anecdote about that 82-83 event. So the Rasmussen and Carpenter paper had come out in 82. Right in the spring of 1982, something was happening in the Pacific, but it wasn't developing along the coast of Peru. It was kind of happening, and it seemed SST anomalies were out there in the Central Pacific, and so there was a meeting it was a climate diagnostics workshop. This used to be a meeting that was held in the US every year somewhere, and it was held at NCAR that year, and it must have been somewhere around June of 1982. And Klaus Wirtke, who was a very famous oceanographer from the University of Hawaii, who was an El Nino expert, every one of these climate diagnostics workshops, he would get up there and give the El Nino outlook, whether there would be an El Nino that year. And I was there in that room, in the main seminar room at NCAR, and we're all waiting to hear what he's going to say about, there was something going on in the Pacific. Nobody knew quite what. And there was the El Chichon eruption, so that was disrupting some of the satellite measurements. There weren't good SST retrievals that were coming out of the Pacific, but it wasn't developing the way that Rasmussen and Carpenter showed. And Wirtke had talked about the buildup of heat in the Western Pacific, and he didn't think that was happening because he deployed these measurements of sea level. He was measuring sea level at Pacific Islands, and he just didn't think, so he got up there and his punchline of his El Nino summary, he said, and he was a German scientist, very heavy German accent, "There will be no El Nino this year." And like 2 months later, it blossomed into the biggest El Nino on record, and so he never lived that down. People for years would kid him about his El Nino outlook was, "There will be no El Nino this year." But then there was this awareness that these El Ninos are all different. And that was just because there weren't enough measurements of enough El Nino events to give you an idea of what was actually going on. And people were still guessing at the processes. And so it was really those formative years. And it was really an amazing coincidence they had the first Southern Hemisphere. And David will remind me that I was not in attendance at that event.
David was.
And David was, because you've been to every one of them.
Yes, and I'm not sure whether you want to transition to those now, Julie, but look, I mentioned a little bit about these set of conferences focused on Southern Hemisphere meteorology, and I'd been very interested in evaluating the sorts of variations that I'd looked at theoretically in my PhD, and then also the teleconnections. Now had a data set of Southern Hemisphere year-to-year and season-to-season variations associated with El Nino, as well as the sort of variability of the large-scale circulation in the Southern Hemisphere. And I gave a paper at that first AMS, or American Meteorological Society, conference on Southern Hemisphere meteorology in 1983. I had really just finished a postdoc position. I had literally just started a lecturer position at Monash University. I couldn't fly from Australia to South America across the Southern Hemisphere. I could only go via Los Angeles and then back south again, multiple stops on the way there and into Brazil. But it was fantastic for me as an early career scientist to be able to talk to a whole bunch of other people who were interested, and it led me to a much better understanding of both Southern Hemisphere variability, talking to Northern Hemisphere scientists, and also the connections, the teleconnections that were experienced over South America, because there were lots of people talking about El Nino and its connections there after they realized that an El Nino was actually occurring. And it led me to better understand the sorts of value of comparing theory, model simulations, and observational data sets. And it's only the power of all of those three complementary approaches that I got better understanding of through going to that conference as a very young early career scientist. was fantastic to me. And as Jerry said, I've been to every one of the Southern Hemisphere meteorology conferences. They've been held basically every 3 years in different countries. The first one was in Brazil. The second one was held in New Zealand. The third one was held in Argentina.
Buenos Aires.
Yep. And the fourth one was held in Australia.
Hobart, right?
That's correct. I organised the fourth one, and I was told by the American Meteorological Society that it needed to be held in Sydney or Melbourne. But I wanted to emphasise that the Southern Hemisphere meteorology conferences should include oceanography. And CSIRO in Australia had just set up a separate or new, what they call division, but it was essentially a research centre on oceanography in Hobart, together with the University of Tasmania. And to emphasise that, there was an international group of oceanographers that were keen to, if you like, connect on Southern Hemisphere oceanography based around having a conference in Hobart. And I said to the AMS, we're not going to run it in Melbourne, we're not going to run it in Sydney, we're going to run it in Hobart. And they had to look on their maps to work out where Hobart was located and did it have a convention centre or a hotel that was big enough to run a conference. We turned out to run the biggest Southern Hemisphere meteorology and oceanography conference that had ever been held, with more than 400 participants, particularly a large fraction of oceanographers that we'd never had before, because the oceans and oceanography is critically important. More important in the Southern Hemisphere than it is in the Northern Hemisphere because of the variations in the oceans and the importance of the oceans in the Southern Hemisphere.
Yeah, so just to finish the attendance story. So David's been to every single one of them. I've been to all but 2. So I didn't go to the first one. I was also an early career scientist. I couldn't get funding to go. Harry Van Loon wanted me to go, and they said, well, you're just this little peon master's person. I had just started my PhD at that time. I was working at NCAR, but I just started getting my PhD. How did you get funding support to go to that as an early career scientist?
That's a really good question that I don't really understand. I think I must have been able to get some travel support having just started at the university, sort of startup money that paid me to go and paid the costs. The really interesting thing was that a Bureau of Meteorology scientist, Michael Coghlan, who was essentially was to become the head of the Bureau of Meteorology's Climate Centre, the National Climate Centre as it was to become called in Australia, was finishing up his PhD, and he went because he'd been doing work on blocking or the stationary weather patterns associated with high pressure systems in the Southern Hemisphere. And so he wanted to go, and I went. We basically travelled together. As he was a much older and more mature scientist, had a job in the Bureau of Meteorology, he sort of suggested, let's go that way. He was right. That was the only way that we could get there and get back again via Los Angeles and stopping over. It was basically a more than 24-hour trip, almost 48-hour trip to go from Australia via Hawaii to get to Los Angeles and then back again.
Yeah. There were some interesting street crimes anecdotes that came back from that meeting too. Harry Van Loon came back with, because you're in Buenos Aires, you know, and here's all these scientists wandering around just being victimized by street crime. So that was an interesting thing. But so I missed that one, the first one, then I missed the one in 2015 in Santiago, and I can't remember why I missed that one. But you did the transition from Morocco to Noumea, right? Were you in Morocco for the IPCC lead author meeting?
No.
Okay, so
not.
See, I should get extra points for that because I think there was 4 of us that did this. So we had an IPCC lead author meeting in Marrakesh in Morocco. And then the very next week was the ICMO meeting in Noumea, New Caledonia. So over a weekend, 4 of us basically had to travel halfway around the world to get to this other meeting. And we all went different routes. So Chris Reason went through South Africa. Anyway, Scott Power went through England. I came back through Hawaii, the U.S. and Hawaii, and there was somebody else came via Australia. So we left Marrakesh, and then spread around the world and then all converged back again in Noumea. So we didn't want to miss that Southern Hemisphere meeting in Noumea. And that's the only one that's been held in the tropics, right?
But more or less, it depends on how far you allow the tropics to extend, because I always say that the tropics extends from the South Pole to the North Pole because it has an influence across both hemispheres. But yes, I mean...
Tropical latitudes, put it that way.
Well, all right, tropical latitudes, yes.
Because that was a landmark meeting, because there was a Pacific Island country. It's the only one that's been in a Pacific Island country.
Yeah, and was critically important because of its emphasis on, if you like, tropical variability. And there's always a local, if you like, capacity building. And the conferences in Africa have been critically important in building capacity in Africa as well on understanding it. There've been more conferences held, follow-up conferences held in Australia and in New Zealand. There was a conference earlier this year, which was more a remote conference version on the Southern Hemisphere Meteorology and Oceanography conferences. But it's really important that they've continued, not every 3 years, sometimes a 4-year gap, but it's been critically important, first of all, in building friendships and collaboration, but also better understanding the connections across the Southern Hemisphere and the similarities and differences in regional climate variations. But some of the big things that have changed have been the improved understanding of the connections, not just between the Northern Hemisphere and the Southern Hemisphere, or between the tropics and the Southern Hemisphere. It's been the modes of variability, like the Southern Annular Mode and its variations, better understanding of the connections between the stratosphere and the lower atmosphere. The Antarctic ozone hole wasn't even being considered in the original Southern Hemisphere meteorology conferences. And then some of the other aspects, climate change wasn't being considered in the original Southern Hemisphere Meteorology and Oceanography conferences. And it was only after the 1980s, into the 1990s, that the Southern Hemisphere climate change, not climate variations, but long-term climate change, started to become an important topic of consideration in many of those sorts of conferences.
Yeah, just one anecdote, an ICMO anecdote. So 1989, the meeting was in Buenos Aires. And so I'd been to the one in 1986 in Wellington, got married right after that meeting in New Zealand. And then 89 was in Buenos Aires. And so I flew down to Buenos Aires, never been to South America, get to the hotel, check in. Next morning, go down to the meeting venue. It's a big ballroom. I go walking into this ballroom first thing in the morning, and all I see is extremely well-dressed women. I thought, I'm in the wrong meeting. I turn around and walk. I'm used to meetings in the US where scientists were all male at that time. So I turned around and walked out, and I went to the hotel. I said, where's the Southern Hemisphere meeting? He says, oh, it's right there in that room. I said, no, that can't be it. There's all these women in there. No, that's it. So I walk in there. Turns out that a lot of scientists, climate scientists in the Southern Hemisphere, especially in South America, are female. And I was just amazed. And it changed the dynamic of that meeting, because it was about 50-50 male-female. And that was the first kind of insight into diversity, the really positive aspects of diversity. So you don't have all these stressed out, hyper-competitive males beating each other over the head. Everything gets kind of moderated a little bit, and you're kind of everybody's getting along better, I thought, anyway.
No, completely agree. And the aspect of that story that I found out at that conference and subsequent ones in South America is that because of the sorts of what would be called high-paid jobs in Latin American countries, and particularly in Argentina, and at that time there was very high inflation in Argentina, it was critically important for the male head of the family, where appropriate, to have a well-paid job, secure job, and earn a good living. And you couldn't do that working in the government, typically, or working in academic areas unless you were a full professor, and often they would have a second income. So women were able to get jobs in the university sector and to get promoted, but men would often work in business. And so working in atmospheric science or in climate science was considered not to be an attractive job for men because they couldn't get enough money. It was a second-rate job, and that was the perception that led to a lot of opportunities for undergraduate students to progress into graduate study, and then the graduate students to progress into ongoing academic careers, teaching and research, and for a substantial period of time in the universities, there might be a male grey-haired professor and a substantial number of mid-career researchers and academics who were women. And many of those have progressed to now be the senior professors in University of Buenos Aires, University of Chile, senior scientists like Carolina Vera, who's now one of the co-chairs from South America Argentina in the IPCC, Matilda Rusticucci, and many others who are just leading the research and climate research in South America and have been doing that for many years. And not all, but many of the senior, men have retired and they've just gone into other jobs.
Well, then somebody pointed out to me, they said, well, think of the two real prominent female scientists in the US. They were Argentinian expats, Julia Pagel and Eugenia Kelly. And so I said, oh yeah, that's right. They are from South America. And so they said, well, that's why, you got no other female scientists in the US. They've come from Argentina, and they're now two of the most prominent female climate scientists in the US. And so it was really an interesting cultural kind of thing.
Yeah, I think my first Southern Hemisphere meeting was Iguazu Falls in 2006, which was, I remember that really positive vibe with so many students from South America. Lots of females and and just how good those Southern Hemisphere meetings I think have been for connecting Southern Hemisphere scientists and understanding of the Southern Hemisphere. So I want to take you back now to our early understanding of the Southern Hemisphere meteorology, and there was a monograph that was produced in, what year was it, David? 19...
Turns out to be, this is the monograph, turns out to be it was published by the American Meteorological Society in 1972. You could make an argument that this interview is the 50-year anniversary of the publication of this monograph. And we've heard Jerry talk quite a lot about the role of Harry Van Loon in a lot of that research. And if we go, and I don't know whether you're going to be able to zoom in on this, but Harry Van Loon was the first author listed and one of the major chapter authors for multiple chapters in this monograph. And Harry, I was lucky enough, signed this monograph for me. I bought it, and I then used his advice. And it's a fantastic book talking. Well, I think it was Harry's idea, together with the editor of monographs, that there was no book, no study that could be used in universities in the Southern Hemisphere on the meteorology of the Southern Hemisphere. Remember, we were talking about the absence of weather analyses, the difficulties with understanding the circulation. What was needed was, if you like, a textbook for universities on what was important and different in the meteorology of the Southern Hemisphere from the meteorology of the Northern Hemisphere, because all the textbooks had the high pressure systems and the low pressure systems going around the wrong way. They were going around the Northern Hemisphere way, and what we needed was a textbook or a book that had the circulation, the weather systems going around, the winds blowing around the high and low pressure systems the way they do in the Southern Hemisphere. This was that book, really helpful for teaching in the Southern Hemisphere, but also really helpful in explaining the differences between the Southern Hemisphere meteorology and the Northern Hemisphere meteorology because of the differences in oceans and land masses between the two hemispheres. And I always make arguments that we have two hemispheres with different land masses, and we can use them as almost like different experiments of what is the large-scale circulation dependent upon the land masses and the oceans and how it affects it. And then I got so interested that essentially 20 years later worked on the second version of this with a US collaborator, and this was finished off in 1998, the second edition, which was essentially 26 years later, with a US scientist. At the time, I was still based in Australia, based at Monash University, but worked and had been worked a lot with the collaborators that I'd met through the Southern Hemisphere conferences in the United States, South America, South Africa, New Zealand, and the US and the United Kingdom. Got them to contribute to different chapters, and it covered essentially much of what was in the original monograph, but now started to have aspects of not just weather variations, but Jerry wrote the climate modelling chapter in this second edition, which wasn't included in the original one. This one has not only a chapter on the stratosphere, but chapter on the chemistry and the Antarctic ozone hole as well, and a chapter effectively focused on Antarctic science as well.
What was the chapter you were on?
I was on the general circulation chapter, I think. I'm sure that's what I was on. So I was the editor, but the chapter that I was on was the general circulation. I wasn't on the climate variability, and there wasn't, I think, I'll have to check, live action shoot. There was a chapter on climate change.
Yes, but I think it's very focused on paleo.
Yeah, a lot of paleo.
But guess who was the climate change lead author?
I know, we just looked at it, I forget.
Phil Jones. Phil Jones from the University of East Anglia and Rob Allen. And it was climate change and long-term climate variability. Paleo, exactly.
So yeah, there's lots of, I guess, updates in that. I mean, I think it's still astounding how much was understood in that 72 monograph, right? And then it was updated with all this extra data that you had in 98.
Yeah.
But now, 25 years later or so.
That's correct.
A lot has changed.
Well, it has, but it's also important to recognise that now, if you like, 24 years after this update, there are plans going ahead to come up with an update of the second edition. It will not be published by the American Meteorological Society due to not intellectual property considerations. It was just the funding and the charging that the American Meteorological Society was going to impose in terms of either sponsorship or funding or costs. They now realise that monographs are not a commercially viable concern. For the American Meteorological Society as a book publisher, it's much easier to go to one of the mainstream book publishers. And I think the next volume, Southern Hemisphere Meteorology and Oceanography, will not just be focused on meteorology as the first edition, and the second edition will focus on that as well as climate change.
And Julie is the lead author of the climate change chapter.
And I've wrote Jerry in already to help.
Yep, which is great. That's fantastic. And
I'm going to do the preface.
I'm not sure if it's going to be called the preface or the foreword, but I'm going to do a little bit of the history, both of the Southern Hemisphere Meteorology Conferences and the Southern Hemisphere Meteorology monographs, that history and how it links together.
Yeah, and it's led by Andrea Tichetto, who's in Australia, and Terzio Ambrizzi in South America, and Tando Nadarana, who's in South Africa. So yeah, really fantastic Southern
international collaboration. Yeah.
So just my final question, I guess, is thinking now, you had this experience as early career researchers, you've now had many years of climate studies, and I was fortunate to start interacting with both of you in the mid-90s. And at that time, the frontier of climate research was really, I guess, about coupled modelling. I think I was working as an honours student in the greenhouse group, led by Bryant McAvaney at the Bureau of Meteorology. And I know, Jerry, you remember Bryant from back then, and that his model was really instrumental in sort of starting to think about climate modelling, wasn't it?
You know, this is one of the really major achievements of Australian climate science, is the so-called Australian spectral model. And so Bill Burke, Kamal Puri, Bryant McAvaney, I remember who else was working on that.
Those were the main ones, but in terms of the weather analysis, it was Bob Seaman who was working on the weather analysis system. and several others as well. John LaMarshall was working on the satellite data and satellite interpretations and things like that. But the climate modelling was separately done in Australia. There was a Australian spectral model, and then there was a Barry Hunt and Hal Gordon grid point model that was running not directly in competition, but actually it was in competition. And eventually a decision was made that it was not sensible to run two separate climate model efforts, one in the Bureau of Meteorology and one in CSIRO. And look, there's an interesting, how would I say, organisational politics of which one was going to be chosen. And in the end, they chose neither. They went and effectively both organisations decided they needed to select a modelling system that could be supported and fit and suit both weather forecasting and analysis as well as climate modelling and research.
Yeah, because I think it was a real computational breakthrough using wave numbers, spectra, and using that as the computational base as opposed to breaking the globe up into grid points. And you could do these spectral calculations much faster and come up with really pretty good depictions of weather and climate. And so at NCAR, we got kind of heard about this Australian spectral model and started inviting these Australians over to NCAR. So Kamapuri came, Bryant McAvaney came, I think Bill Burke came at some point. And NCAR took the version of the Australian spectral model and made that the first community, or not the first, one of the first versions of the community model to serve the US university community as a climate model that everybody could use. And so I think that was a really a big achievement for Australian climate science, coming up with that new climate model that got used by other organizations around the world.
And I think when I was there in 94, 95, it was, I think, or even a bit earlier, it was looking at the first ENIC run of that model and comparing it to ERBI data. I remember that was my project. But then I think when I was there doing honours, it was the Greenhouse Group, it was Bryant McAvaney, Rob Coleman, Scott Power, and they were doing one of the first couple of models runs that didn't have flux correction, I think. And then I know I went at NCAR, you were one of the first groups to do that too.
Yeah.
So that was the frontier back then, from my biased perspective. But what do you think now, 2022? What is the frontier of climate research?
Well, for me, it's initialized multi-year predictions. I mean, we've developed climate models into very complicated Earth system models where you're basically trying to have every single thing that's going on in the climate system included in the model. So now we have biogeochemistry, ecosystem components, very complicated land surface, atmospheric chemistry, aerosols. And so we use those to do these longer term projections to get climate change out to the end of the 21st century. But as there's more efforts going into trying to reduce emissions, to try to mitigate some of these effects, the emissions reduction targets aren't going to kick in for maybe another 10 or 15 years, and that's being optimistic. Hopefully that is going to happen. But in the meantime, we're in an adaptation situation. We have to adapt to whatever's going to happen, and that what we're adapting to is some mixture of how this climate system is responding to things like increasing greenhouse gases in combination with these internally generated modes of variability that affect the weather from day to day, week to week, month to month, year to year, decade to decade. And so to really help us give information on what we're going to have to adapt to, we can start to model out these kind of Earth system models we used for these long-term projections. We use them in a different way. We start them out at a particular time with a specific observed state of the climate system, for example, say last year, and you run them forward for maybe only 10 years. And you try to predict the time evolution of regional climate over the next 10 years to give you an idea of what it is each country or region is going to have to adapt to. And so that, to me, is the big scientific challenge now.
And for me, it's similar to what Jerry said, but as Jerry was talking about, the sorts of climate change variations determined by the greenhouse gases that are already in the atmosphere, and the locked-in greenhouse gas emissions will mean that the sorts of climate scenarios, projections that we've got, have effectively locked in global warming of 1.5 degrees above pre-industrial levels in the 2030s, and 2 degrees of global warming by 2050, almost irrespective of what we do in terms of emission reductions. And then the warming will only stop at 2 degrees and potentially be reduced back to 1.5 degrees by 2100 if we rapidly get to net zero emissions later in the next decade and a half. But if we don't, we're going to have even higher global warming beyond that. But what is critically important is to understand, as Jerry was saying, not only the sorts of interactions between climate variability and climate change, but to do that at spatial scales, which are important for the impacts of climate change that we're seeing now and we'll see even more of between now and 2050. And so we're really going to need high spatial resolution climate model simulations at spatial resolutions that resolve the thunderstorms, resolve the impacts of climate change on the weather systems, and do that for many different impact areas. We've seen in Australia extreme rainfall, which has been made worse, we don't quite know how much worse, by human-caused climate change. We've seen extreme temperatures and bushfires, and the impact of both extreme rainfall and then flooding needs hydrological models. For bushfires, we need fire models embedded in the climate models at spatial scales that are potentially hundreds of meters if you want to forecast what's going to happen to the fires in steep topography. We need agricultural models to be nested within the climate models, or at least make use of the output of climate models. And these sorts of collaborations between simulating the weather, simulating the extreme weather, taking into account climate change, and then using that for a whole range of applications, whether it's human health applications, whether it's natural ecosystem applications, whether it's ocean ecosystem applications, and what's going to happen to coral reefs, what's going to happen to fisheries, what's going to happen to flooding, what's going to happen to our cities and represent the urban. There are so many cross-disciplinary applications. It's not just climate science, it's many other discipline areas that I think are critically important to work with. Climate scientists aren't necessarily the best people to provide information about the impacts in all these different areas, and we know that weather and climate is already impacting all those different areas.
Fantastic. Well, thank you very much for joining me today to talk about the early years of Southern Hemisphere meteorology and climate, and I'll leave it there.
Thanks a lot.
Thank you, Julie.